of this workshop and the invitation. I think I just checked my email, and the last SMC workshop I was in was in 2015. So that was in Paris, I think, unless I've forgotten. So it's been like 9 years. I'm going to talk about mixing time as a conditional backward sampling particle filter. Hopefully, title makes sense. If the title is new, I will talk a little bit about what the algorithm is, but the algorithm is actually very old. The algorithm is from 2010. And this talk is mainly about analyzing how good that algorithm is, because it's thought to be quite good. This is joint work with Joona Karjalainen, Matti Mihula, who are in Jyväskylä and also here. And Joona will give a poster about a related project this evening or this afternoon, and Sumit Singh, who's in Wollongong, and unfortunately, it's a bit far, I think, for him to come to this workshop. Okay, so what is the conditional backward sampling particle filter? Well, the conditional particle filter, was proposed in Christoph Arno and Roman Hollenstein's red paper in 2010. And in one of the discussions of that paper, Nick Whiteley, who is also at Bristol actually, suggested, why don't you do this backward sampling step? So that's what this talk is about. This slide is just describing what the sort of target density that we are considering is when we look at the conditional backward sampling particle filter. So it has this kind of form, just written as a density for simplicity. You have some initial distribution, M1, and then you have these sort of potential functions, which G1 and up to GT, and you have these Markov transition densities. Okay, so in a way, it's kind of like you have a Markov chain defined by M1 and all of the rest of the MTs, and then you sort of reweight the law of that Markov chain according to these potential functions G1 up to G capital T. Okay, and for those, since this is an SMC workshop, I feel like I won't need to describe too much, but obviously these M's and G's are also the kinds of components that you will actually use to define your SMC algorithm. And I will do that on the next slide very quickly. Okay, and while there's nothing to do with HMMs in my talk, this is sort of thought of as the smoothing distribution in an HMM setting, and sometimes you want to draw samples or some expectations with respect to the smoothing distribution would then be written, for example, like this. Okay, and so if you want to do that, then one thing you can do, which is more classical, is just to run a particle filter, which targets this distribution. And if you have enough particles and you do some kind of backward smoothing, there are different types, then you may get good approximations of this type of expectation. Okay. Alternatively, and this again was from the 2010 discussion paper, you can define a pi invariant Markov kernel, which essentially involves running a conditional SMC algorithm, and you can just keep iterating that. And in particular, when you use backward sampling, there's the opportunity to use a much smaller value of capital N than you would have to do if you wanted to just approximate this using one particle filter, apply some smoothing. I don't know if Nikolai is here, but he's worked recently on papers where they do big particle filter and some kind of clever smoothing. Okay, and of course, in cases where, for example, there are unknown static parameters, then this sort of pi invariant Markov kernel can be used within a sort of Gibbs or Metropolis within Gibbs type component Markov chain. Okay, so that's known as particle Gibbs, and there you can see even more clearly that it's useful to have a way to sample or to define a pi invariant Markov kernel rather than just rely on a separate kind of massive SMC algorithm. Although that exists, of course, as well. That's the SMC squared type algorithm. Okay, so this is the algorithm. I've tried to make it quite simple. Whenever I talk about weights, the weights always have exactly this expression, so I won't talk about them too much. One of the things that's nice about SMC algorithms is they're quite simple. In a conditional backward sampling particle filter, the first thing you can do is set sort of x1 to t0 to be the reference path, which is the sort of initial state that you're going to sample this is supposed to be sampling from this Markov kernel at x1 to t star. That's what we call the reference. First thing you can do for this particular version of the algorithm is just put x1 to t star into the first index of the path of a particle system which you'll produce. the rest of the particle system, you sample n times from M1 independently. And for time t is equal to 2 to capital T, you just sample from this mixture distribution. Okay. Where the weights, as I said, are they depend on those G's, and these are the same M's and G's that were used to define the target density on the first slide. Okay, so you just repeatedly sample from this mixture distribution. I call this, we call this in the paper, zeta T capital N. Okay. So that's great. And once you do that, you've sampled the whole particle system. It's very much like a particle filter, except for the existence of this reference path, which does sort of pollute everything else. We then do the backward sampling step. That just says, let's sample an index from a categorical distribution with probabilities proportional to the weights at time t. And then going backward, you just sample indices according to the weights. So BTI, this is going to tell me how much I want to put weight on sort of particle I at time t. The weight at time t going forward matters, but also the transition density associated with the XTI and the point that I've already picked while I'm going backward in time. I understand that if you're not familiar with the algorithm, it may be difficult to follow, but hopefully there's a simple kind of forward pass using SMC, and then there's a backward pass where you sort of pick according to sort of quite appropriate probabilities going backward. Okay, and then at the end, you output sort of chosen path. You look at your particle system, and you just output the x1, j1, and xt up to xtjt. Okay, if there's any questions, I've made a silly error, then please let me. Okay, so this is, it's also equivalent probabilistically to ancestor sampling, at least in the form that I've given here, which was proposed by Linston, Jordan, and Schoen, 2014. So what do we know about the CPF? So the CPF is actually this algorithm, but without the backward sampling. Instead of doing backward sampling, it uses something called ancestral tracing, which I won't get into the details of. Okay, but it's sort of, it was the thing that was proposed in the original discussion paper, and is simpler to analyze. So without or if you ignore the fact that you're doing backward sampling, because everything that's true for the CPF that I say here is also true for the CPF with backward sampling. That algorithm was analyzed by Chopin and Singh, Linston and others, and also Christoph and Maddie and myself at pretty much the same time, although the publication date is much later for us. So Chopin and Singh in particular show that it's a positive operator, which is kind of useful for getting convergence bounds. In the paper with Christoph and Maddie, we showed that basically if your weights are uniformly bounded, little t basically, then your Markov chain is uniformly ergodic, which is quite nice, and it's almost an if and only if. Well, it's still a conjecture, I guess. Okay, but the main takeaway, and most of these results give similar things about uniform ergodicity, but the interesting thing is that under strong mixing, which I will discuss soon, it is this kind of result essentially says that you need to take the number of particles proportional to capital T if you want to control the sort of mixing of your Markov. Okay, and that's pretty much just necessary if you're not going to do backwards. Okay, but this gives a sort of order T squared time complexity under strong mixing, and also a lot of space. Okay, and as Axel said yesterday in his talk, of course, backward sampling changes the picture completely. Okay, but until I think until this work, it was actually unclear theoretically why or how to see that it's changed the picture completely. So what do we know about the CBPF? Well, I guess we've been a little bit obsessed, but Maddie, Summit, and I showed in 2020, right, that you don't need to increase n with capital T if you're doing backward sampling. Okay, and we got some, I think, nice results, but the results today should be better. Okay, so in that case, there's some sort of threshold number of particles where as long as you use enough particles, or basically for any rate of convergence that you want, you can pick the number of particles large enough such that this is true for all t, right? So you don't need to pick the number of particles depending on t. It only depends on sort of the strong mixing assumptions, and you can get this kind of result. But of course, because here there's an alpha to the t, it means that the actual mixing time bound that you would get will be order capital T, right? So you will still have an order t squared time complexity. The main benefit is that you can see that you don't need to keep increasing the number of particles. Okay. But today, after more work and involving a new member of the team, Joona Karjalainen, we were able to show that there exists, and again, it's the same story. There exists a sort of minimal level of number of particles, such that if you have more than that number of particles, you get this bound. And here, there's just a t there, right? There's no alpha to the t. The total variation bound after k steps of your CBPF is t times lambda n to the k, where lambda n is basically like 1 over square root n, right, with some logarithmic factor. Okay, so you can get basically anything up to that kind of dependence. So now the mixing time is only log t. Okay, which means that instead of a t squared time complexity, we now have a t log t time complexity, which of course is much better for very large t. And finally, we can say that at least under strong mixing, we can see why the CBPF is behaving so much better than the CPF, which matches also practically. Okay, so how does it work? So the argument that we use to actually prove these kind of bounds involves coupling, which it was first initiated in the Chopin and Singh paper to use coupling to analyze these things. And I think some of the other results didn't involve coupling at all. We're back to coupling because it seems to be useful. It's a very natural thing to do if you're trying to bound total variation convergence. If you're not familiar with coupling, a coupling of random variables x distributed according to mu and y distributed according to nu is a joint distribution gamma, such that if x prime and y prime come from gamma, then marginally x prime has the same distribution as x, y prime has the same distribution as y. Okay, and one reason this is useful is because the coupling inequality says the TV distance between mu and nu is basically upper bounded by the probability that x prime is not equal to y. Okay, and this is actually this is an equality if gamma is a maximum, right? So in a way, TV distance or the optimal TV distance optimizing over couplings. The TV distance is given by a sort of probability that two random variables are not equal when using the optimal coupling. And we will use a lot of optimal couplings today, which is why I mentioned this gamma max. Okay, and one thing that is useful to know is that there's a procedure of unknown origin, but certainly talked about for a long time, and in Thorison's book, is that it's easy to sample from a maximal coupling if you know the densities of mu and nu, and you can sample from mu, for example. Okay, and it's just a rejection sampling algorithm, and it's very fast. Well, it's as fast as it is to compute the densities. Okay, so the main step in implementing the CBPF, just like the main step in implementing any particle filter, is sampling from this distribution several times, right? This is how particle filters work. So again, I've said this is Z to T. It's this sort of mixture distribution it's a mixture distribution, right? You've got your weights, you've got your Markov kernel, you've got your particles at the previous time. Okay, so in a coupled particle filter, you need to sample, we will want to sample from a joint distribution where you sample from a coupling of these two distributions. Okay, but basically this is xt 1 to n comes from a product distribution. You sample n times from this, right? So it's like this. And x tilde t 1 to n will be the sort of second set of particles that come from a particle filter with a different reference, right? They will come from z to tilde tn to the n, right? Again, it's another product distribution, and this is the corresponding mixture. Okay, and the idea is we want typically to make those particles to be as similar as possible, right? So that we can achieve some kind of coupling. Okay, so this is how the coupled conditional backward particle filter algorithm works. And I know it may not be obvious if you haven't looked at these kind of coupling of Markov chain proofs before, but the idea is we want ideally that x1 to capital T is equal to x tilde 1 to capital T after several steps of running this, the corresponding coupled Markov chain. But you should see that essentially you're running the same algorithm. You're just doing some kind of coupling steps. So you set the references, you don't have much choice in that, that's purely deterministic. In the first step, you will sample the x1i's all from M1 independently, but you're also able to set all of the x tilde 1i's to be equal to the x1i's. There's no problem there because you're just supposed to sample them from M1, right? They come from the same distribution, so it's easy to do that coupling. Okay, but for the subsequent times, we're going to sample from some kind of forward coupling of the two product measures. Okay, and then when we do backward sampling, we're just going to use maximal couplings from these discrete distributions. That's the same as people have done in the past as well. So we're not changing that part of the coupled CBPF algorithm as well, but we're going to do something different in this part. Okay, so going backwards, you just try to pick the same index. You keep trying to pick the same you just keep trying to pick the same indices during the backwards sampling process. Okay, and at the end, so that it's clear, you output x1 to t, x tilde 1 to t. These are just, again, given by the x's at the corresponding indices that you chose during backward sampling. So I hope that's clear. There are three couplings that I'm going to talk about today. The first coupling is the coupling that we used in previous papers and also was even used in the Chopin and Singh paper. Okay, that's the index coupled CBPF. In that case, I'm not going to write exactly what gamma IIC is, but that comes from sort of trying to think about the sampling from that mixture involves sampling from the indices of the mixture components, right? And then sampling from the mixture components. So in index coupling, you try and pick the same indices whenever you can. And if the particles are actually the same at those indices, then you will succeed in actually coupling. Okay. So you try to pick the ancestor indices the same. If the values of the particles at the same ancestor indices are the same, then you can do this equal thing. And otherwise, you just do some kind of independent evolution. Okay, and that does work, and we were able to prove something in that context, but basically, very rapidly, the sort of particle systems become totally different. Okay, so only when. So it's still true that when you do this kind of coupling, if all of the particles are the same and the references are the same, then the particle systems will continue to be exactly the same until there's one different reference. Yeah.
Just a question here. If the ancestors are different, but the points are the same, you couple?
If the ancestors are different, yeah. So the way I've written it, I do say that you will do that, and in reality, you could do that. But in practice, we don't usually do that because on a general state space, they would never be the same. So
yeah, but
it wouldn't really make much difference, I think. It could make a difference actually on a discrete setting. That's true. Yeah. But on a general state space, you'll find that the number of coupled particles will sort of decrease exponentially fast as soon as the references are different. And that's what in some sense leads to this kind of linear mixing time. I've got a picture after this one. Well, after the next. So something else you can do, which is very exciting, which is why we got back to this project actually, is that instead of doing that, you can sample independently several times from the maximal coupling of these two distributions, okay? And that's definitely feasible. And this was also proposed to do by AJ and you in a different context, I think in a multi-level type context. And it allows spontaneous coupling. So it solves this problem where you don't just sort of have the number of coupled particles decreasing and then go to zero, but then stay at zero. You can spontaneously start coupling some particles as the algorithm progresses. Unfortunately, it's very difficult to actually analyze what happens with this algorithm, even though it's a very interesting one. So what we end up analyzing today, which is what we call the joint maximal coupling, which it probably looks like it's better, but it's not necessarily better, is that now we sample from a maximal coupling of the two product measures, okay, which is also feasible to do. Okay, it doesn't cost. It costs it's an order n squared computation, but it's certainly feasible. It doesn't take that long and it's not too big. Okay, so you can contrast this. So this is what I'm going to talk about for most of today. This is what we call joint maximal coupling. This is where you sample the particle systems at each time from a maximal coupling of the two product measures. Okay, whereas if you were doing the independent maximal coupling that I talked about in the last slide, that would be sampling from a product of the maximal couplings. Okay, and in particular, with this joint maximal coupling, there's a high probability, or there can be a high probability, that all of the particles are coupled, all of the non-reference particles are coupled. But this tends to have a lower probability that, for example, one set of particles is coupled. Okay, but it basically means that you're going to kind of have a all or nothing. Like all of the particles will be coupled when you implement this in the standard way, or none of the particles will be coupled. Okay. So here's a picture of what happens when you run the CBPF, and in this, in black is the sort of uncoupled references after running several iterations of your Markov chain, right? So up here is that's the number of iterations of your CBPF, of your coupled CBPFs, and in black, if it's black, it means they've not coupled, right? And if you run with the index coupling, you tend to see that the things start to couple progressively from the left of your reference. And that's what we analyzed a few years ago. Okay, but you can kind of clearly see that the amount of time it takes to couple will be linear in the total time here on the length of your capital T in the target density. Whereas if you look at the joint maximal coupling, then what happens here is you start off all uncoupled. I guess I don't show the first initial state. Then you see some things have coupled, and then quickly you start to see that these kind of couplings start happening all over the place, and you're only waiting for the last bit to become coupled, right? Which you can kind of think of as demonstrating why you could expect an order log t, or an order log t time for all of the states to be coupled. Okay. So what's the main result? The main result is that if you use for this forward simulation a joint maximal coupling, if you let capital B be the total number of particles after you've chosen your new reference with backward sampling, this is the number of sort of unequal, or the number of uncoupled particles, uncoupled states, that's capital B. B star is the number of uncoupled or unequal reference states that you put into the algorithm. Then after each iteration, you get that the expectation, if n is large enough, right, there exists a lambda n that's independent of t, such that the expectation of B is less than or equal to lambda n times B star. Okay, and lambda n itself is kind of like 1 over root n with some log squared n on the top. So if you think of your Markov chain, you think of B, so this is like B0 would usually be capital T, B1 is after one step of your CBPF, B2, and so on. Then it's easy to see that the probability that BK is greater than or equal to 1 by Markov inequality, less than or equal to the expectation of BK, which is less than or equal to lambda n to the K B naught. Okay, and from that, you can already deduce that your mixing time will be bounded by T lambda n to the K. Okay, so for a fixed n large enough, your mixing time will be ordered log T. Okay, does that make sense? I will try and go through some of the more important parts, the more important, more interesting arguments in the proof for those people who are interested. Okay, so first, of course, there's strong mixing. I'm not going to talk about that too much. Of course, there are some assumptions that we need in order to get these kind of nice results. They're obviously quite strong. They're very standard. They've been used for a long time. I don't know who invented them. Maybe it was Pierre, but maybe they existed before that. Okay, so I'm not going to talk about it too much. Basically, they usually mean that you're on a compact state space and that your potentials are lower and upper bound. Okay, so one of the key ingredients to the kind of proof is that we're going to have two references and we're going to define something called holes, right? And basically a hole is just a place where the two references are not equal. Okay, and then we're going to define a distance to the nearest hole. So, you know, basically you're going to have your kind of your series of times. If t, so here's how you can define a hole, but you know, you don't need to read that. The main thing is that dt is just the distance to the nearest hole. So if I'm thinking about time step t, right? If t is in hd, which is the set of times for which dt is equal to d, then basically you're going to have an unequal reference particle either here or here, and all of these references will be equal. Okay, that's all it. And the idea, hopefully, is that what we want to say is that if t is in hd with d large, that means I'm far from a hole, which should mean that it should be easy, hopefully, to make those references couple in the next iteration, or you should have a reasonably high probability that they will couple in the next iteration. Okay. Okay. So that's what a hole is. I think one thing that is worth mentioning is that the reason this joint maximal coupling is easy to deal with is because instead of analyzing a whole particle system where you have capital N particles in both systems, in fact, we end up analyzing a very simple system, just in some sense, a 3T dimensional system. The only thing we care about, and we kind of don't even care about this that much, but it's easier to write it this way, we care about when are the references equal, okay? What are the times at which the references are equal? We care about what are the times in which all of the non-reference particles are equal. So we call that being full, right? So when are the particle systems basically the same, ignoring the reference? And then CT is when are the output particles equal? Like the new references that you generate from your algorithm. Okay, and this is what we end up analyzing. This system, and we don't need to think about all of the sort of intricacies of which particles are coupled or which particles aren't, and so on. Okay. So again, this will be sort of mainly intuitive. So okay, so we're using this joint maximal coupling. It has the nice property that if it succeeds, then all of the particles that are not reference particles become equal immediately. And if it doesn't succeed, typically all of the particles are different. Okay, at least if you do a simple implementation. Okay, so we think of FT, that's this event, non-reference particles are equal, and we'll call ET the complement of FT, which says empty. And you know, while in general it wouldn't be true, for this kind of algorithm, it's actually you're usually either full or empty. Okay, so there are some nice features associated with this particular coupling. So the first one is that it's likely to stay full. Right? So if you're full, you're likely to stay full. And that appears in this bound. So first, if you're full and the references are equal at the next time, then you're definitely going to stay full. That's just generally true for any kind of coupling that you would probably use. But it's also true that if the references are not equal, then there's a probability that's over 1 over square root n that you will uncouple. Right? So you're likely to stay full if you are full. Okay, and then the second feature of this coupling is that if you're not full, you're likely to become full in order log n time. Okay, so it won't take too much time, hopefully, for you to become full. Especially we're thinking of the situation where n is typically fixed, right? N doesn't grow as t. Okay, so we can say this in this way, but basically, the details don't matter too much. It's just that, you know, you're definitely going to become full eventually in only a relatively small number of steps. And if you want to get more details on how this works, you should see Jona's poster, which is about a slightly different problem, but essentially it's the same kind of arguments in this case that we've had to specialize. Okay, the idea is that, well, one of the ideas that we had for this trying to show the coupling is that, in fact, if you have time uniform stability of particle filters, it should be the case that even without doing any kind of clever coupling, all of the particles should be having similar empirical distributions. And therefore, the predictive distributions, or those zetas, should also be similar. And then the question is, are they similar enough that you can couple all of the particles? And it turns out that it's true. They do become similar enough that you can couple all of the particles. Okay. I won't talk too much about that. You can talk to Yona if you want more details. So the third point is that so we've talked about how if you're full, you're likely to stay full, and if you're not full, then you're likely to become full in a certain number of steps, okay, in log n steps. And now finally, the last bit for the forward coupling is that if you're far from a hole, then the sort of unconditional probability that you will be empty at time t is quite small, right? Because in the end, you get this kind of alpha to the d over Sn, well, with a 4. But basically, as d increases, you become sort of less and less likely to be empty. And if you're not empty, you're full, okay? So, you can ask questions about the details, but I think that's my attempt at making the important elements of the proof intuitive. Okay, so now after you go forward, then you go backward. In fact, the sort of analysis of the backward sampling phase is not that complicated. The main thing to know is that if you're full, right, then you're reasonably likely you're reasonably likely. So if you're full at time t, you're coming backwards from time t plus 1. You want to basically see if you're going to choose the same particle going backwards, okay? And under strong mixing, you are reasonably likely to do that if you're full, and you're very likely to stay coupled if you are already coupled going backwards. And that's what these kind of bounds tell you. So if the references so if you're not already coupled, then basically you have this epsilon bs that tells you you're pretty likely to couple with this probability epsilon bs. It might not be very close to 1, right? But basically every time you go backwards, if you're full, you have this epsilon bs chance of coupling. On the other hand, if CT plus 1 was holding, which means you've already coupled, you've already chosen the same reference going backward at time t plus 1, then it's very likely that you will remain coupled, okay? Even if the references are not equal, but if the references are equal, then it's certain that you will. Okay, and the holes argument in itself is actually very simple once you have all of those ingredients. Of course, I've left out many technical and counting details, but this is just the same definition I gave before. B is the total number of unequal references that you're going to output from your algorithm. B star is the input number of unequal references. And you can say, well, what is the expectation of B? Well, you can just take the expectation of the sum, but you can think of a partition of T into, what, we've got these sets HD. HD is the set such that you're D away from a hole. So you're just partitioning the space of times, right, into how far are you from a hole. So that's how you can do this decomposition. Okay, and then here you just do very simple bounds where you look at this, the size of those sets. How big is H0? H0 is equal to B star. How big is HD? HD is a set of times where you have where your distance D from a hole. Well, that's going to be less than or equal to 2 times the total number of holes. Okay, and then you just replace all of those indicators by probabilities, right? And then you take the suit. Okay, so all we need to do to kind of complete our argument is to bound the probability of not being coupled in a way that can depend on how far you are from a hole. Okay, and after making use of all of those intuitive things that we talked about, you can get this kind of total bound on the probability of not being coupled, right? You just look at the probability of not being coupled. These are the uncoupled references going backwards, yeah? So what is the probability of being uncoupled? That's the probability of being uncoupled at time t and it being empty at time t, plus the probability of being uncoupled at time t and it being full at time t. And here you can see that you have something that looks pretty promising because you have D's appearing in the exponent in both situations. Okay, so I guess it's not interesting to go through all of these calculations, but in the end, you're going to do this kind of infinite sum over all D's, but because your D's appear in the exponents, this is going to end up being summable. Okay, so in the end, you get that lambda n is less than or equal to some constant times log squared n over square root n. Okay. Okay, so the final points. I'm happy to go back and talk to people about specific aspects, but the final points are just that we've gone through what the CBPF is. We've gone through this coupled CBPF. We've talked about how using the coupled CBPF, you can prove how long it might take for the two coupled systems to become equal, right? How many iterations of the Markov kernel you need for them to become equal, and that's order log t. And that implies that the CBPF, so not the coupled CBPF, just the normal CBPF we all, that many of us will have actually implemented and used in practice, that mixes in order log t time, okay? This is also optimal, so you can't do better than order log t time, at least for a general class of problems, because it's easy to come up with a simple example where you must take order log t time to mix. Okay, like a very favorable example. Okay, other things you can ascertain is that because P is a positive operator, then its spectrum is contained within 0 to lambda n. So if you're only interested in results on the CBPF, then the coupled conditional particle filter is only a device, right? You don't actually care about the computational complexity of it. Okay. Obviously the assumptions are strong, even though they're kind of typical mixing assumptions that you use to prove things about particle filters. It seems reasonable that the result should be somewhat more general. Something like that should be true in more general terms, but it's very hard to conduct an analysis in the absence of those kind of conditions. On the other hand, if you're interested in coupled conditional particle filters, which you might be because you want to run some kind of unbiased estimation algorithm following, in particular, the more recent paper by Pierre Jacob and co-authors, then you may be happy to know that you can actually run this algorithm. It doesn't actually cost that much, and it may be much better for you if you use this kind of joint maximal coupled or the index maximal coupled forward coupling. Okay, so if you want to use these kind of algorithms for unbiased estimation, then you do really run the complete algorithms. Or the joint maximal coupling or the independent maximal coupling, the computational cost per iteration of the Markov kernel is order n squared t. That's because it costs order n squared to evaluate all of those densities, right? In order to do the coupling. Whereas the CBPF is only order nt. Okay. On the other hand, if you were to use the independent index coupling or a joint variant, it would cost order nt, but it gives you order capital T mixing time or meeting times. Okay, and so we did do some experiments for lots of different choices of parameters for some problems. And indeed, if you have a very small capital T, then maybe you're better off using independent index coupling because it's cheaper in terms of capital N. But once T is pretty big, then you really probably should be using one of the sort of more sophisticated order n squared T coupling algorithms. Okay, and that's because it's only going to take log T iterations, right? So it's like comparing these two things, nt squared versus n squared T log T, but with n fixed, right? You only need to pick a large enough n, and then you don't need to increase n anymore. Okay, so the final thing that I want to say is just that the independent maximal coupling is actually probably better than the joint maximal coupling. It's kind of clear, even when you implement it, that you can see that it has more chance of working outside of strong mixing, right? I mean, we've done experiments with JMC, even in sort of some Gaussian state space models, it still works, right? But in general, it might not work that well, whereas the IMC will work, right? But it's very difficult to prove something about that system because it has a sort of random number of coupled particles at each time, and it's very hard to come up with a good technique for proving that the number of coupled particles eventually reaches the total number of particles. Okay, we did try a few things, but they turned out to be dead ends, at least in the sense that, yeah, they didn't work out. But it is also true if you're really interested in having something where there are proofs, then you can actually run some kind of hybrid schemes where most of the time you're using the independent maximal coupling. Every sort of k steps you run the joint maximal coupling, or if all the particles are, if all the known reference particles are equal, you use the joint maximal coupling, right? Then you can still have the result, right? But actually, it's probably better to just use IMC in practice. Well, it seems empirically that it's better to just do the independent maximal coupling in practice. And there's no proof that that even works by itself. Okay, so that's it.